Hello, uh, welcome to the live interactive session, and this is the week 3. And this live interactive session is for the course Structural Geology offered by NPTEL. And as per the course content of week 3, we will be discussing about some concepts of deformation and strain. My name is Rajiv Mukherjee, and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. And I am hosting these live sessions for the 12-week duration of the course. So this is the course outline, and in the previous 2 weeks we already covered the basic concepts of structural geology, which was the week 1, and then we discussed different kinds of structural elements, measurements, and stereographic projections in the last week, that was week 2. And today we are going to cover the week 3 contents of this course, which is the concepts of strain. And this is the live interactive session. I host this live interactive session on each Saturday. Today is the third live interactive session on 10th August 2024, and this is the session link to join this live session. Okay, so about today's live session. So first of all, I will summarize what we have learned in the week 3 of the course Structural Geology. So we learned about the concept of deformation and strain, homogeneous and heterogeneous deformation, rigid body rotation, translation, pure shear, simple shear, subsimple shear, coaxial and non-coaxial deformation, finite and progressive deformation, strain ellipse and strain ellipsoid, that is in 2D strain and 3D strain. And then we learned about the Flynn diagram, which is an important component of strain analysis, and some techniques of measuring strain from deform markers. And based on the content of week 3, we are going to discuss the following things. First of all, we will discuss about measurement of strain and certain applications, especially one-dimensional and two-dimensional strain analysis. I will emphasize on some methods that has not been taught in the course, but it is important to know about them. It is an extra addition to the course, like you can say that. And then I will also discuss about the concepts of deformation matrix, how we analytically solve the problems regarding stress and strain. I will just provide a glimpse of that, and I'm sure that in the week 4 content you guys are already knowing about what is stress and how the deformation matrix is associated with the stress. But for today's discussion, we will only focus on the geometrical aspect of the deformation and how using the classical coordinate geometry we can put together an equation that can describe a deformation matrix. And then as per our problem solving session, we will also delve into some conceptual problems related to strain and deformation. We will solve them. Finally, I will conclude and summarize the discussion session, and I will also briefly talk about the plan for upcoming live session. Okay, so talking about strain analysis. So why strain analysis is important? That is the first and foremost thing we have to understand, is that in nature we do not see the deformation that is continuously taking place. I mean, we do get the signals, like from the GPS signals, we get to know about the plate movements and how the subduction is taking place, how an oceanic ridge is expanding, right? These kind of things are the living or real life examples of deformation. However, these things are so minute that we cannot comprehend them visually, We just have to rely on the data. But in nature, whenever we go to field doing structural geological field works, we see various kind of structures. May it be a brittle structure like fault or slicken lines, or joints or fractures, or it can be some ductile structures like fold, boutinage, lineation, foliation, etc. These kind of things are very common in the field. Now, the most important part is that the component of ductile deformation or plastic deformation, so called permanent deformation in rocks, these things are comprehended through strain analysis. I mean, we have developed some methods through which we can actually determine how much strain has been accommodated to that particular rock unit we are studying. Now, the rock unit, it can be a single exposure or it can be a regional scale deformation as well. But however, we have developed some geometrical and analytical methods to come up with a pretty good solution about estimating how much strain has been accommodated during a phase of deformation in a particular area. Now, this estimation of deformation, it can also vary significantly based on the scale of observation. So when we are talking about microstructures, say for example, we are observing some thin sections, in that case, the strain that we estimate might be very much different from the strain that that we try to estimate from field observations, right? But within all of these complexities, one thing we try to make sure is to estimate that the nature of the deformation, whether the deformation is homogeneous or heterogeneous, and if so, then how it is varying from one place to another, or how is it varying from one phase of deformation to another. So as a structural geologist, when we are dealing with strain, we have to be very careful about deciphering these episodes of deformation. We have to uh, decouple the different uh, episodes of deformation that are entangled with each other, and as a result we are seeing a cumulative effect of multiple phases of deformation in a rock. So first of all, I mean, first and foremost, the most important thing for a structural geologist is to do in a field is to decipher and delineate different episodes of deformation. Now, once you identified that there are n number of deformations had taken place in a particular region, then you go from one set of deformation to other and try to estimate how much strain variation has occurred between from one episode of deformation to other. So the analysis of strain, it can occur in three different dimension. So first we have the one dimensional strain analysis, which involves particularly studying the linear features on planar fabrics, right? So by analyzing one dimensional strain, we try to estimate the amount of stretching or shortening that has taken place in a particular rock mass or a rock assemblage, right? From 2D strain analysis, we try to analyze the development of a preferred orientation and how much change in the aspect ratio has taken place for different kinds of uh, rock unit. It can be a mineral grain, it can be different kind of strain markers, right? So the purpose of 2D strain analysis is to actually justify or to estimate the intensity of deformation. Whereas for a 3D strain analysis, like the Flynn diagram, The main purpose of this analysis is to understand the nature of deformation, whether it is a constrictional strain regime or whether it is a flattening type strain regime or it is a plane strain condition. So these kind of strain, these type of strain conditions or strain regime can be differentiated using the three-dimensional strain analysis, where for two-dimensional we mainly focus on to understand the intensity of deformation, and for simple one-dimensional strain analysis we just go for understanding that during whether there is a stretching or extension or shortening or compression. Okay, now in the lecture you have already had a good grasp on the three-dimensional strain analysis, that is the Flynn diagram. But in today's discussion session, we will not be covering the three-dimensional strain analysis, but we will focus on two most commonly applied methods for one-dimensional strain analysis, and particularly this method, which is called the RFI method for two-dimensional strain analysis. Okay, so going on to the next topic, which is ideal strain markers, right? So for going into the definition, we can say that strain markers are natural objects with well-defined undeformed or initial geometry, which can be utilized to estimate the strain accommodated in a deformed particular object in a rock assemblage, right? So for analyzing the strain, it is pretty obvious that we cannot see when did the deformation even took place. We can of course go for radiometric dating, different kinds of tools are there, but the only thing only thing we can estimate is the age of the deformation. But we actually did not see or visualize the deformation event by ourselves. Therefore, we do not actually know from what initial state the deformation started. For example, I am observing an elliptical shaped table or a mineral grain or rain imprint or whatever geological structure it may be. It can be a fossil as well in some rock exposure. Now, to my understanding, I can quickly assume that okay, so initially this might be a spherical object that has deformed to this kind of elliptical object. But assuming this thing is assuming this thing is pretty much erroneous because we do not know the initial shape of the object. So that means we do not have any reference based on which we can say with confidence, okay, so initial shape is like this, and from that particular shape, the shape changed to this, and therefore this is the pattern of the deformation that took place in this region. So for entangling that part, we need some references based on which we can actually estimate the type and the degree of deformation. So for that we need strain markers. So strain markers are, as per the definition, some natural objects with well defined undeformed or initial geometry. So this is the very much important part. To be a strain marker, we need to know the natural shape of the object. Natural undeformed shape of the object. And not only that, that particular object, whether it be a fossil, whether it be some kind of mineral aggregate, or any kind of rock lineation, whatever it may be, that particular thing has to occur in abundance within the rock mass we are trying to deal with, right? Because as you can see, we will go there, go into deeper analysis. For estimating the strain, we need a very large number of data to actually minimize the deviation. or the standard deviation of our results or the analysis. And so that is why strain markers should be some objects that are present in a very large number, so that we can analyze each and every one of them to actually estimate the strain, right? So there are 6 classical shapes or classical types of strain markers, which are called the ideal strain markers. So what are those ideal strain markers? So first is the original spherical or equidimensional forms, for example such as ooids, right? Reduction spots, some microfossils like foraminifera and radiolaria, mineral aggregates in hornfels igneous rocks. So these kind of things, they are either spherical in their original form or they are equidimensional. And most importantly, when they occur in nature, they do not follow a particular orientation. They can occur randomly when they are not deformed. So random orientation along with spherical or equidimensional shape, right? This is the criteria for this kind of strain marker. Next is original circular cross section on a known surface. For example, pebbles in sedimentary units, rain imprint structures, sin sedimentary deformations like convolutes, and some kind of ichnofossils. So geological structures that we see in the field, they are exposed in different planes. So essentially, any object that is three-dimensional, we generally observe these kind of objects on different planes, and these planes are the cross sections of the rock mass. Now ideally we have 3 perpendicular cross sections which we generally follow for kinematic references, which are xy plane, xz plane, and yz plane. So for properly analyzing the strain along a particular plane of orientation, if we get these kind of cross-sectional views on that particular plane for which the orientation is known, then we can use that initial shape as our reference for calculating the strain. Like sin sedimentary deformation structures, convolutes have a pretty good uh, spheroidal shape in 3 dimension, but in 2 dimension, when we observe them in the exact plane, we see that they show a concave downward droplet like structure. So this is the original undeformed shape of a convolute, and we know that we have some undeformed exposures. We find them, we take measurements and photographs of these kind of undeformed structures, and we use them as the reference. Now ichnofossils are interesting things because ichnofossils are basically some structures like burrows or any kind of footprints or any kind of imprints left by the animals like tracks. So these kind of things are also preserved in sedimentary units, and they also have some preferential directions. Like when an animal is digging a burrow, it will always dig the burrow in vertical direction. So if we cut the cut a sedimentary unit perpendicular to its bed, we can we can expect to get the full burrow structures or the signofossils. Now, due to some sort of deformation, this burrowing structure may be interrupted or even got broken. These kind of things can happen, and based on these interpretations, we can estimate how much strain has taken place. Right. Next is original non-spherical objects which approximately have shape of elliptic which approximately has a shape of an ellipse. Okay, so Pebbles and conglomerates and weirds in the sedimentary unit, they are pretty much the ideal example for this kind of uh, objects, which has not a spherical or circular initial shape, but an elliptical initial shape with a certain aspect ratio. Now, the fourth one is original linear form. Most of these are like fossils, and we have a pretty good example of this is belemnite. This is a kind of cephalopod fossil, and their shells are preserved in sedimentary matrix. They are long tubular structures. They have rod-like body. I mean, their anatomy is a rod-like structure, and due to deformation, these shells fossils, they either get compressed or they get extended, and from their stretching and compression or stretching or shortening, we can actually estimate the strain. Another example is the cross stratification. Cross stratification strata, they generally occur as some linear features when we observed on the exit plane of the kinematic reference, and then we see some inclined linear features. These are the cross stratifications, and from their deformation in the linearity and their shape, we can estimate the strain. Another important part is bilaterally symmetrical objects such as brachiopods, trilobites, echinodermata fossils, which have bilateral symmetrical shape. And due to deformation, such as like coaxial deformation, these bilateral symmetry can get distorted. And from their distortion, we get to calculate the asymmetry in their shape. And the degree of asymmetry that has been accommodated or accumulated in these kind of fossils are the direct indicators of the strain. Right? And finally, we have known initial angles like cross beddings. They make a constant angle with the primary bedding plane. Mud cracks, the mud crack imprints, they have constant angle varying from 60 to 120 degrees, and that angle you can use to calculate whether there is a accumulation of strain or not. And for microstructural studies, we see euhedral or prismatic crystals like quartz, and we get them as reference uh, reference grains to actually see whether there is a development of uh, SPO. Generally, we talk about strain analysis, we say SPO, or that is called shape preferred orientation. And we also look for crystallographic preferred orientation of these kind of grains to actually estimate the intensity of plastic deformation suffered by these mineral assemblages. So for microstructure, we look for just a second. So we look for SPO, which is also known as shape preferred orientation. And we also look for CPO, which is crystallographic preferred orientation. So for microstructural perspective, we use these two quantification, which is one is the SPO and the other one is the CPO to estimate the strain from thin section scale. Okay, so this was all about ideal strain markers. Now we will go to one dimensional strain analysis. So as we talked about what is the purpose of one dimensional strain analysis, so basically it is to get the data about how much stretching or how much shortening has taken place. So for one dimensional strain analysis, we mainly rely on two classical methods. One is Ramsey's method proposed by John Ramsey in 1967 and another is Hossen's method which was proposed in 1979. So first we will discuss about Ramsey's method. So in this figure, these are some fragments of a belemnite fossil. So this is the shape of the belemnite fossil. One side is concave and another side has a bullet like shape. So overall, if you just join these fragments, you will get the initial length of the fossil, right? So what happened is that in between these fragments, there are sedimentary matrix and the entire rock mass has stretched, and because of this stretching, these fragments occurred. I mean, the entire shell got fragmented into different pieces, and in between them, the rock mass, which was ductile enough when the deformation was taking place, it, it has flown in between these fragments to fill the gaps. So for analyzing the strain, we generally call these part of the fossils as fragments and the matrix in between them are the gaps. So for Ramsey's method, the initial length L is taken as the sum of the length of the fragments. So for example, there are 4 fragments and each of them we measured the length, right? So for F1 we will measure the length from here to here. For F2 it will be here to here, right? I can draw it. So for F1 the length will be from here to here. For F2 it will be here, and similarly for F3 and F4, right? So the initial length is taken as the sum of the length of the fragments F sum and the final length, which is L dash, is taken as the total sum of the length of the gaps and the total sum of the fragments as well. So for Ramsey's method, we take the total length, I mean the final length after deformation, which includes the length of these fragments and the length of these gaps as well. Now, according to Ramsey's method, if we follow that there are 3 gaps and for that we have 4 segments. So for n number of gaps and n plus 1 number of fragments, we have the total length of the gap I is equal to 1 to n, where gi is the individual length of these gaps, and if sum, it is the summation of length of individual fragments, and it will of course go from 1 to n plus 1, and then we will have fi, that is the length of these individual fragments. And using this formula we can actually come up with the formula for quantification of stretch. Stretch is, as we have gone through the weekly content, you already know that stretch is L prime over L. L prime is the final length and L is the initial length, and L prime is basically G sum plus F sum. That means stretch is 1 plus the gap, the total length of the gap, and divided by the total length of the fragments. Now as you know that stretch is equal to 1 plus E, and this E is the elongation, right? So if E is the elongation, then as per our formula, the elongation must be the sum of the total length of the gaps by the sum of the total length of the fragments. So this is the formula for that, and we also know that quadratic elongation lambda has a formula of a square. So if we know the length of these individual fragments and the length of their individual gaps, corresponding gaps, we can calculate the elongation, the stretch, as well as the quadratic elongation. Okay, so this is Ramsey's method. Now we have another method which is called the Hossain's method, which was proposed in 1979 by Hossain. Now, from the previous method, say for example Ramsey's method, the photograph or the image or the schematic that has been shown in here, this one, this is very much textbook like feature. It is an ideal structure of a belemnite. But during deformation, or in case of natural rocks, it is quite hard to get very ideal shape. Most of these fragments would be, I mean, of irregular geometrical shape. We, we can't even define a geometry properly for that. And for measuring the length, it becomes pretty much hectic. From which end to which end you will consider the distance, and there is angular distortion also involved in these cases. So measuring the distance just so simply is not an option for real life samples. And to give an alternate to this problem, Hossain has uh, incorporated a minute but important modification into this existing formula. So the final length is taken as the distance between the midpoints of the two end fragments, and the initial length is the sum of the fragment lengths between these 2 points as we talk. So the previous formula told us that you have to consider the length from this end to this end. This gives you the total length. But Hossain is saying no. So may be the geometry, it is always easier to find a central spot or a midpoint for each of the end fragments. So once you identify these midpoints, you consider the distance in between them, and that is your final length. Now then, how many fragments we are considering? So this is half of a fragment, this is one, this is two, and this is another half of a fragment, right? So altogether we are considering three fragments and three gaps. In case of Ramsey's method, we had four fragments and three gaps, but following Hussein's formula, we came up to three fragments and three gaps. So for n gaps, this will be n number of fragments, not n plus one fragments. For n gaps and n number of fragments, we have the formula again. For G sum, the formula remains the same, but for F sum, or the total length of the fragments, we have Fi plus Fi plus 1. We consider the length of the next fragment as well, where I is 1 to n, not n plus 1. But during the calculation, we consider Fi plus 1. As you can see, we have taken this half and this half. Together, it is a whole fragment length extra is added with the two fragments F2 and F3. So this formula justifies this excess fragment length. And similarly, we can calculate the stretch, which has this formula 1 plus E. So this is the elongation. And similarly, we can calculate the quadratic elongation, lambda. Okay. So strain analysis in one dimension, it is pretty easier because we often observe this instantaneous stretching taking place within the rock masses, and these deformed or stretched pebbles or fossils, they are good indicator or strain markers for one dimensional strain analysis. The important purpose of this one dimensional strain analysis to actually identify the amount of stretch that has taken place, as well as to find if there are any preferred orientation of this stretching. I mean, for preferred orientation, I mean that if this linear feature along which the extension or the stretching has taken place, it has a particular trend. So we just measured the trend of this stretching axis and the amount of stretch that has taken place. So this is how we identify the principal axis of strain. So one dimensional strain analysis is particularly useful for getting the information about the principal axis of strain. So one dimensional strain analysis is useful to determine the magnitude of strain and the orientation of principal axis of strain. Okay. Now we will see 2D strain analysis, and in the third video of week 3, you have already seen about, or you have already learned about the Fry method, which is commonly known as the center to center method, right? Fry method or the center to center method. Now this Fry method or the center to center method is pretty much based on the concept of anti-clustering of statistically large number of data points, right? You generally create a void, elliptical void, by constantly joining the centers of the reference ellipse to the center of the elliptical shapes that you have been provided with. And this void generally represents the strain ellipse in two dimension for a given plane of orientation. But the idea behind this center to center method, it considers a very profound assumption that initial markers are all circular, but that is not always the case. Initial markers, as we have already learned from the ideal markers, the initial shape of the marker can also be elliptical. And it is not necessarily that each and every marker, even prior to deformation, they would be random. I mean, there can also exist a preferred orientation as well, even prior to deformation. So, just by assuming that all these objects that are now deformed, they were initially circular in cross section and they were randomly oriented, would provide a very biased estimate of strain, certainly pretty much erroneous. Now, to avoid these kind of assumptions, this method known as the RFI method was developed, and the idea behind this RFI method I will describe it. So for example, we have in this coordinate system, we have an object which is initially ellipse, and this is the long axis or the major axis, and this is the short axis or the minor axis. Okay. And this major axis makes an angle of theta with the reference line. So this is any reference line in your system, right? So consider this as the undeformed state. Now we have imposed a certain deformation into this material. The deformation essentially, if the deformation is asymmetric, then there is a high chance that the deformation is non-coaxial. Certainly it is non-coaxial. Also, it is under the influence of subsimple deformation or subsimple shear. So if we just impose a subsimple shear to this elliptical marker with an original orientation of theta with a reference line, now after deformation, we get this shape. The, the marker obviously has stretched. The long axis has increased. So if the initial long axis was L1, now the long axis must be L2, and L2 is greater than L1, whereas the short axis, if this is S2 and the short axis was initially S1, then S1 is greater than S2. So this is the relation that we expect from the deformation of an ellipse. And also we see a change in the angle. So initially the angle was theta. So this is the angle theta, and now due to deformation, this reference line has also rotated to an angle of phi. So theta minus phi is the amount of rotation imposed into the system. Imposed into the system during deformation. Okay. So this is how we generalize the deformation feature, that is quite different from the center to center method. In center to center method, we assume that all the markers are perfectly horizontally aligned. There is no angular preference. Not horizontally aligned. I'm sorry. Though the markers are all randomly oriented without any kind of preferred orientation, and all the shapes are elliptical. But instead that we say that no, markers can possess a certain initial orientation, that is theta, and they can also certainly possess some initial ellipticity into them, into the system, right? So advantages of this RFI method, that it is applicable for initially oriented and elliptical objects, which is otherwise impossible for the center to center method to provide the strain analysis using this condition with least amount of errors. That is not possible. Secondly, it considers the ellipticity and the angular orientation of each marker, that is otherwise also absent in case of center to center method. Third point is that it provides an estimation of initial ellipticity and the magnitude of strain. And finally, it is a robust graphical analysis method, and a graphical analytical method, and it produces less amount of error. So that is why RFI method has more advantages over the conventional center to center method for strain analysis. Now let us have some understanding or theoretical basis for this RFI method. So consider this is a coordinate frame XY. Now this is the elliptical marker. Prior to deformation, right? This is the reference line. Okay. The initial angle is theta. This is long axis 1, and this is the short axis 1. Now this red color ellipse, this is the reference ellipse. Around the strain marker that provides an initial condition. And when the ellipse is deformed, when the marker is deformed, the outer ellipse or the reference ellipse, that is also deforming. And the deformation of this reference ellipse or the changes in the aspect ratio of this reference ellipse will be considered as the strain ellipse itself. So deformation of the reference ellipse is considered as the strain ellipse. Okay, and as you know that the initial angle theta, it changes to phi, and now we have changed long axis to as well as the short axis to, and the reference line has also rotated. So we consider three different things. One is the deformation of the reference ellipse, the second is the deformation of the marker, and third is the angular change of the reference line. Based on these three observations, we estimate the strain from RFI, or we estimate the strain through this RFI method. Now, one thing is important to note is that during practical exercises, phi, this is measured as the angle between the long axis of the deformed marker and a reference line along clockwise direction. So, this is the reference line and this is the long axis, right? So we measure the angle clockwise, not this angle. Okay, I mean this angle won't be considered. Only this angle will be considered because this is clockwise. Now, what do we measure? For theoretical consideration, we measure theta, phi, and one thing important that is to know that ellipticity of an ellipse is basically the aspect ratio of the ellipse, and aspect ratio is nothing but the length of the major axis divided by the length of the minor axis of the ellipse. Now we have these strain parameters that we commonly use in the RFI method. So first of all is the theta, which is the initial angle of the reference line. Phi is the final angle for the reference line. Ri is the initial aspect ratio of the elliptical marker. Okay. Rf is the final aspect ratio of the elliptical marker. I mean, after deformation, of course. And Rs is the aspect ratio of the deformed reference ellipse. Right. So this deformed reference ellipse is the strain ellipse. Therefore, by estimating the ellipticity of the strain ellipse, we can have an estimation of the strain. Okay. Okay. So based on the formula, I mean, based on the theoretical consideration of different angles and different aspect ratios, we yield certain formulas. One is the tan of 2 phi, which is expressed as this 2 into this Rs is the aspect ratio of the strain ellipse multiplied by the initial square of the initial aspect ratio of the strain marker minus 1 into 2 theta divided by this uh, arrangement. And once we know tan theta, tan of 2 phi, sorry, we can estimate Rf, that is the ellipticity or the aspect ratio of the elliptical marker after deformation, and this Rf can also be expressed as a function of theta and phi through this formula, what is tan square phi multiplied by 1 plus Ri square tan square theta. minus r square into tan square theta plus ri square divided by this denominator to the power half. That means this the square root of this value. Now from the maximum value of phi, the initial ellipticity and the strain can be calculated through the following analytical equations, which is sin 2 phi max is equal to Ri minus 1 by Ri divided by Rs minus 1 by Rs, and Rf, which is the final aspect ratio or ellipticity of the elliptical marker, as a function of phi max only, and that can be represented as Rs plus 1 by Rs divided by Ri plus 1 by Ri plus square root of Rs plus 1 by Rs whole square, Rs plus 1 by Rs divided by Ri plus 1 by Ri whole square minus 1. So you take square root of this, and from this we get the analytical value of Rf. However, for practical purposes, an estimation of numerically maximum and minimum value of Rf can be estimated as Rf max is equal to Rs multiplied by Ri, and Rf mean, which can be represented by either Ri by Rs or Rs by Ri, whichever is greater, right? So these are the theoretical considerations from which we get these reduced values, and these reduced formulas are actually helpful for practical analysis of strain. Now, how we actually measure the strain through RFI method? So for example, you have these deformed structures like this. Okay, so these are some, this can be either deformed or stretched pebbles, they can be different kind of mineral structures, the quartz grains, they can also be different kind of fossils, whatever it can be. So these are some deformed markers. So from a set of these markers, we initially find the length of the long axis like this, and we measure. So for example, this is one deformed marker, right? So we measure the length of the long axis from this point to this point, and we also draw a reference horizontal line from where we measure the phi angle clockwise, and we maintain this measurement technique uniformly throughout each and every of these markers, right? So for some markers we will have higher values of long axis and short axis ratio. We also measured the short axis as well. So we measured the long axis and short axis and the angle phi for each and every of these ellipse, right? So first we prepare a table like this where we put the serial number of each of these elliptical shapes or deformed markers. Then we calculate the long axis, then we calculate the short axis, and we calculate RF, because this is the final result that we are observing, right? So this must be the final phase of deformation that is yielding this RF, that is the aspect ratio of this elliptical markers, right? So we calculate the ellipticity of these deformed markers by by taking the ratio between the long axis and the short axis, that gives us the value of RF, and we also calculate the value of phi, okay, from creating a horizontal line and taking the clockwise angle between the long axis and the horizontal line. Now in a graph we plot the phi, which can range from 0 degree to 180 degree along the y-axis, and along the x-axis we plot the values of RF. Now if we have data points greater than 30, so if we have more than 30 data points, we will eventually see that plotting the phi and RF values for each and every of these corresponding deformed markers, we will find that the values are eventually clustering in one place. So we have to identify this cluster. Then we take the midpoint of this cluster, extrapolate these values vertically and horizontally to the x and y axis respectively. So this will create an intercept here and here as well. So the value we are getting, the intercept of value is the RS, and intercept value at y along y axis is phi s. So the cluster being projected to the x axis or the axis along which we have plotted the RF. So it gives us a threshold value of the ellipticity, which is basically the average ellipticity of all these deformed markers, and their mean orientation or average orientation as well. So phi s, this is the orientation of the, or we can say as it is the mean orientation of the uh, long axis of the strain ellipse and RS, this is the mean aspect ratio of the strain ellipse it signifies the amount of strain. Okay, and using the formula this one or this one, for example Ri, we can get it as Rf max by Rs. Now where to get the Rf max? We see which is the highest value of Rf max. We take the mean and get the highest value. This is Rf max and this is the value of Rs. So we simply divided the value of Rf max by Rs and we get the mean average, or sorry, I mean mean initial ellipticity of the deformed markers. So we can estimate Ri, and then we can also estimate Rf, and we can also estimate the amount of strain accommodated during the deformation, and we can also estimate the orientation of the long axis or the principal axis of the strain ellipse. Okay, so this is how RFI method is applied in case of deformed markers. So it is quite clear that the process of deformation, it involves not only change in shape and size, it also changes angular orientation, right? So to understand the entire process of deformation, we only need the information regarding the amount of rotation or the angular changes, the amount of change in shape or deformation, and the amount of translation. So rotation, deformation, and translation all together will give us the cumulative strain in a rock or any kind of deforming material. So we just need to get these three informations to estimate analytically how much strain has been accommodated in a deformed unit. And for that, we rely on the concepts of deformation metrics. So, for example, we have an initial shape of a square and we have a point P here with initial coordinates of x1 and x2. Now we have imposed a certain deformation into this square that resulted in the formation of this parallelogram, right? So this parallelogram has several components, right? So the center point remained here, but this point, which was initially here, it has moved to here. This point moved to here and here. So we have different type of movements within this square object that resulted in this shape of a parallelogram. And we also get the new coordinates small x1 and small x2. So D11 is the point, this point. Now this point has moved up to here. The distance to which it has shifted times the initial coordinate is this part, which is D11 x1. And this point, it has moved to this point, and this component is called D12. So D12 times x2 will give me the amount of displacement that has resulted, or amount of deformation that has resulted in the formulation of this new coordinate system. So D11 is the coefficient, x1 is the uh, material space coordinate, x2 is also the material space coordinate, plus t1, this is the amount of translation. So together with these components, we get the new coordinate of small x1, which can be expressed as d11 capital X1 plus d12 into capital X2 plus t1. So t1 is the translation component along this direction, and t2 is the translation component along this direction. Similarly, for x2, small x2, we can also derive an expression such as d21 capital X1 plus d22 capital X2 plus t2, right? So if we write this thing in a form of matrix, we will get a matrix, a column matrix x1, x2 is resulting in a square matrix of d11, d12, d21 and d22 times another column matrix of capital X1 and capital X2 plus this one. So this is the spatial matrix, and this is the material matrix. This is the translation matrix. Sorry. And finally, the coefficients of this material matrix is the deformation matrix. Right. So in mathematical terms, this transformation assigns or maps each material particle if a coordinate has px1 capital X2 to a spatial point p small x1 and small x2 through the components of d11, d12, etc. So p was here, which was capital X1 and capital X2. Now p is here, which has small x1 and small x2. So from capital X1, capital X2 to small x1, small x2, how much it has shifted, right? So it was initially like this, now it is like this. So this much amount of, so if this is the initial shape, we can surely say that this much amount of extra, uh, what can I say? So this is the amount of extra movement, translation as well as rotation occurred to the point P that resulted in this new coordinate. So for that coordinate, we have this x1, which includes the component d11 and d12, and for the coordinate x2, we have the components d21 and d22. So d11, d12, d21 and d22, these are the coefficients that tells us that how much amount of strain is imposed on each and every of these coordinates, I mean along these coordinates, that could translate and the point P from its initial position to its final position. So this is something like an information or an algorithm delivered to a system. It is like a process delivered to a system that, so such that using this process or this information, one can translate from one point to other. So this d11, d12, d21, d22, this determines the path of the translation of the point. And that is why, since it is determining the path of this deformation, this is called the deformation matrix. And for the information, if d12 is equal to d21, it is called the symmetry. And if d1 equal to d21, then this is called asymmetric deformation matrix. Okay, so this was the concept of deformation matrix. Now we will solve quickly some questions. uh, I mean some MCQ problems related to strain and deformation. So the first question says that the relationship between X, Y, and Z of deformed pebbles in a conglomerate, right, and the axial planar cystosity, which is S1, is such that on S1 options are given: X and Z of pebbles always lie, only X of the pebbles lie, Y and Z of the pebbles lie, and option D, X and Y of the pebbles lie. Right. So the question is asking that if there is a foliation plane and you see that there is a deformed conglomerate on that. So if this is the foliation plane and you are seeing a deformed conglomerate like this, so of course you will have the long axis and you will also have the short axis, right? So the question is asking is that how the long axis and the short axis of this elliptical pebble is actually oriented with respect to the kinematic x, y, and z directions. So to solve this problem, we can look into the a schematic of a shear zone. So we can see that in a shear zone, this is the direction of shear, right? So from a perspective of kinematic framework, so this is the direction of shear, and therefore this is the displacement plane where we see the maximum displacements. So therefore this plane this is the shear plane, and shear plane is analogous to the foliation plane. So of course you are seeing that this is the foliation plane, and we are seeing stretched pebbles as well. Now if you follow, the general rule of thumb is that the displacement plane will always contain x and z, and in a kinematic framework we always assign x greater equals to y and greater equals to z for finite strain, right? So in that sense, xz plane will always contain the maximum stretching direction and the minimum stretching direction, and that is why any section which is lying on the xz plane or which is parallel to the xz plane, here we will of course see the linear features. And if we observe the xy plane, which is this plane, which is also parallel to the foliation plane, we will observe the planar features such as the pebbles, right? So following this diagram, we can now easily answer that the relationship between the x, y, and z of the deformed pebbles in a conglomerate and the axial planar cystosity is such that on S1, option D will be correct because x and y of pebbles lie on the S1 plane. So if the long axis of the pebble is equivalent to x and the short axis is Y. On the section, this is the S1 plane. Then we will see these pebbles like this. Okay. Okay. So the next question is, plane strain condition is indicated by option A, x is greater than y, z equals to 1. Option B, x is equal to z and altogether greater than y. Option C is x is greater than z, y is equal to 1. And option D is x is greater than z, greater than y, and altogether greater than 1. Now, for plane strain condition that we know, if this is our initial cube, right? And if we assign certain directions such as this is x, this is y, and this is z, so the deformation for plane strain will happen like this. So there will be stretching along x, shortening along z, but there will be no deformation along y. So this is the classical condition for plane strain. So the deformation shape, it would look like so. Y will remain constant, x will be greater than z. So along this direction, shortening, and along x direction will be stretching or extension, and there will be virtually no change along the y direction. So y will eventually remain 1, and since extension is greater than shortening, therefore x will be greater than z, and that would indicate that x greater than z, y is equal to 1 is the right answer. So this is the condition for plane strain deformation. Okay, so this was the second question. Now moving on to the third question. Question is, cyst represents a material which has mechanical property as option A, homogeneous and isotropic, option B, homogeneous and anisotropic, Option C, inhomogeneous and anisotropic, and option D is inhomogeneous and isotropic. So schist is a rock which is contained by foliation plain, right? So these are the foliation planes. This is X, this is Y, and this is Z. Right? Now it is obvious that for the this schist to occur, compression must have taken place like this, right? So just as we have seen in the shear plane, shear zone. So these shear planes are the XY planes, and these are the foliations, like shear plane. So the deformation event took place because of compression like this, right? And this kind of compression produces these foliation planes, which are like this, the shear plane essentially. So in this case, we can say that the compression direction is like this. So, and another property is that the foliation plane, or sorry, foliation or the cystosity is a penetrative structure, and they are formed during a single phase of deformation. So one set of foliation will always be developed during only one set of deformation, right? And they will be perpendicular to the direction of the compression. And since all the minerals which are essentially the micaceous minerals or phyllosilicates, they basically form the schist, the schistosity or the foliation planes, right? So it is quite obvious that since the foliation planes are essentially defined by the phyllosilicates, they will be compositionally homogeneous throughout the planes. And if there exists a compositional homogeneity on that plane, that would eventually mean that there should be a mechanical homogeneity as well. So foliations are mechanically homogeneous on the plane, right? However, so if we are observing layer parallel mechanical strength, it will obviously be homogeneous. But if we observe layer perpendicular material mechanical strength, that would be different, because these layers occur in alternate compositions. So layer parallel strength is not equal to the layer perpendicular strength. That means option option B is correct, that the foliations are, or the cystosity are homogeneous and anisotropic structures in terms of their mechanical strength or mechanical properties. Okay, moving on to the next question, which is, it says that symmetric boudinage is usually produced by extension of a competent layer embedded in a incompetent matrix, and chocolate tablet structures is the result of a deformation where the bulk finite strain ellipsoid shape k value is given by option A, k equals to 1, k less than 1, k greater than 1, and D, it is none of the above. So if we see the Flynn diagram, we will see that the plane strain condition has k is equal to 1. The constriction phase or the constriction space has generally k greater than 1, and for flattening we have k less than 1. And now this structure, this is the sorry this structure, it is the chocolate tablet boudinage. So as you can see that the chocolate tablet boudinage is occurring in the flattening type strain, and therefore since in the flattening type we have k less than 1, so option B will be the correct answer. So chocolate tablet boudinage occurs within the flattening regime. Okay. Okay. So question number 5 tells us that at high pressure and temperature, rocks begin to develop permanent ductile strain under stress. It happens when the stress reaches the following. Option A, the ultimate strength. Option B, shear strength. Option C, fracture strength. And option D is the yield strength. So if we observe the stress versus strain curve, for any ductile material, we will see that the curve follows this kind of pattern, either this or this or this kind of pattern. in each case you can observe that there is a linear segment where the stress increases linearly with strain. So this regime is called the elastic regime, and beyond the point where the curve becomes nonlinear, this point demarcates the yield strength of the material. Now when the material crosses the yield strength in high pressure and high temperature, it shows ductile deformation that results in this non-linearity between stress and strain. Therefore, when the rock begins to develop permanent ductile strain, it has to cross the yield strength, and therefore option D is the correct answer, that it reaches the yield strength. Okay, question number 6 tells us that in the following illustration, unit circle and resultant strain ellipse for three types of deformation have been illustrated along with the resultant field structures expected for the deformations. Choose the correct options, or choose the correct option that matches correctly the deformation type with the resultant field structures. So in this case, we have the reference circles with opposite diameters, right? So this was the initial case A, and then we have produced a strain ellipse which is like this. That means this circle has been compressed to this ellipse. So compression is both along the long axis and the short axis. That means both along the long axis and short axis, compression structures will occur. That means both the long axis and the short axis will experience folding, and that will match with 3. So A will go with 3, right? Now the second one tells us this was the initial state. We have gone to this state. So we have compressed along this direction, but we have extended along this direction. So while compression along this direction will produce a fold, extension along this direction will create Boudinage, right? So in this case, B matches with 2. So C, we have the circle which is expanded in both the direction in an elliptical shape. So that means extension on both the direction, it will obviously produce Boudinage along both the direction. So C will go with 1. So in that case, A3, B2 and C1, that is option D, is the correct answer. Okay. Coming to the next question. Identify the lines of no finite strain LNFS in the following figure. Option A, LNFS is marked by only dashed line in the figure. Option B is LNFS is marked only by solid lines in the figure. Option C is that LNFS is represented by both dashed and solid lines. And the last option is there are no LNFS in the figure. So for progressive deformation, we know that lines of no finite strain is that the rotation of any line which are not, so for progressive deformation, any line which is not parallel to the principal axis of strain, they will rotate, right? But there are four such lines which are, one is any line that is parallel to the principal axis of strain, the long axis and the short axis. And if we join the intersection points between the strain ellipse with the initial circle, so we will get two lines through this point of intersection during progressive subsimple deformation. So in that case, these two lines as well, they will not rotate because this intersection point will remain constant. I mean, not they will obviously rotate, but their length will not change. So line of no finite strain means, say for example, you have this initial circle, right? Now it has been deformed to an elliptical shape like this, right? So you have these four intersection points. You join them diametrically opposite, so you will get these two lines. Now with progressive shear, the ellipticity of the strain ellipse will change, and so does the point of intersection. But eventually, if you join them, you will find that the lines are not changing their magnitude. The only reason is because the strain ellipse is constantly intersecting with the perimeter of the initial circle, and since the diameter of, or the radius of the perimeter, radius of this initial circle is fixed, the intersection points will not change their length. And that is why the dashed line in this figure, they represent the line of no finite strain. And since option A says that LNFS is marked by only dashed line in the figure, so option A is the correct answer. Okay. Question 8 says that if a rock is subjected to a constant strain rate of 1 into 10 to the power minus 15 per second, calculate the value of stretch and quadratic elongation over a duration of 100 million years. So we have strain rate here, which is d epsilon dt 1 into 10 to the power minus 15 second inverse. So total strain or elongation E is equal to strain rate into time. So that is 1 into 10 to the power minus 15 per second into 100 million year. So we can calculate the terms of in terms of second. So that is 1 year is 365 days. That means there will be 365 times 24 times 3600. So this is the amount of second per year. So for total this much amount, we will have 100 million year. That means 100 into 365 times 24 times 3600 to the power 6. Okay. So this is the amount of seconds. So this will be the total strain or the total elongation. So once you calculate the total elongation, you will calculate the stretch as 1 plus elongation and quadratic elongation. So this is stretch and quadratic elongation as lambda is equal to 1 plus e whole square. Okay. So by putting these values, you can calculate yourself. Just have to check that how this value is coming and multiply it with the strain rate, and you will get the total elongation, which is then easy to calculate for stretch and the quadratic elongation. Okay. Option 9 says that, question 9 says that choose the correct answer, and there are 4 options given. First is in a progressive pure shear, all material lines rotate during the course of deformation except those parallel to the principal axis of strain. So this is a correct statement, right? Option B says that in progressive simple shear, all material lines except those parallel to the shear plane rotate during the course of deformation. In a simple shear, so you have, if you place a line like this, eventually the line will rotate like this, because during simple shear it will, any line will rotate in such a way that it will make itself parallel to the shear direction, or in turn the shear plane. So option B is also right. Option C tells that the terms irrotational and coaxial are not synonymous. Neither are the rotational and non-coaxial. Yes, of course, because coaxial deformation can also involve rotation. Any line that are not parallel to the principal axis of strain will also rotate during pure shear, which is actually coaxial. And any line that are parallel to the shear plane or the shear direction will eventually will not experience any kind of rotation in simple shear, even when the simple shear is a mode of non-coaxial deformation, right? So option C is also correct, and therefore option D is the correct answer for this question, is that all of the above statements are correct. Okay, last question. We are already near 6. So this question tells us that a foliation plane strikes north 40° east. The apparent dip of this foliation plane along north 10 east. Okay, so first of all, we can say that this is north and this is east, and strike of the plane is north 40 east, and we have measured the apparent dip of this plane along north 10 east. Okay, so we are already getting an information that there is a deviation of 30°. Very good. So if the dip of the foliation plane changes to 60° during another phase of deformation, then calculate the amount of shear strain suffered by the foliation plane. Okay, so first of all, we need to calculate the true dip. So we know that the true dip will be somewhere along this direction. Of course, it will be plus 90° to this, but we need to get the dip amount. So if we consider the true dip amount, delta, trend theta is 10 degrees, strike pi is 40 degrees, then structural bearing will be 40 minus 10, that is 30 degrees. Okay, so apparent dip which is P is 30 degrees. Then we can use the formula tan of 30° is equal to tan of delta times sine of beta. That means tan delta sine 30°, which is half of tan delta, or tan delta eventually will be 2 by root 3, because tan 30 is 1 by root 3, or delta is equal to tan inverse 2 by root 3. So this is the initial dip amount, right? So we can calculate it as so delta is 49 degrees, and it is also given that the final dip of the plane is 60 degrees. So therefore change in dip amount is 60° minus 49°, which is 11 degrees, right? And therefore the shear strain We know shear strain is equal to gamma, that is tan of psi, that is change in this angle, that means tan of 11 degrees. So if you calculate the value of tan 11 degrees, you can eventually get to the shear strain value. And this is how we can calculate the amount of shear strain suffered by the foliation plate. Okay, so this was all about the third week's discussion session. And for the upcoming, so in this discussion session, to summarize, that we learned about one-dimensional strain analysis, we learned about Ramsey's method, we talked about Hussein's method and their difference, and then we talked about the RFI method and the process of calculating it and how we can apply for practical measurements using RFI method. And then we talked about the concept of deformation matrix and how it is calculated through equations. And after that, we solved some numerical problems and MCQ problems related to strain and deformation. So this was the third week's discussion session. And in the next discussion session, that is on the 17th of August, next Saturday, we will discuss on stress and related problems. Thank you for joining this live interactive session, and I hope to see you all on the next session.